Hello and welcome YouTube, Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Step on inside, and we are reviewing sections 1.1, 1.2, and 1.3 in the Integrated Math 2 Big Ideas Math textbook. If you'd like to follow along with this, there's a PDF down below in the description section, which is probably important for this one because I had to zoom out the PDF page a little bit more to fit the problems in right. They don't go by columns in this one particular page, and it's only one page to look at. 18 problems, and once again, description section, check out timestamps to each individual problem for this set, as well as if you want to see anything else, especially from sections 1.1, 1.2, and 1.3, perhaps take a look in the description section for the playlist for everything Big Ideas Math Integrated Math 2. Now, without further ado, I will go ahead and get started on this Integrated Math 2. Big Ideas Math focuses 1.1 on absolute value functions, 1.2 on piecewise functions, and 1.3 on inverses of functions. So let's go and take a look at anything. And I don't know if they're laid in order. They might jump around. They have the sections on here, if you take a look, where they show number 1 through 3 is out of section 1.1. Describe the transformation from the graph of f of x equals absolute value of x to the graph of the given function, then graph the function. So absolute value functions have the v shape naturally to them, and f of x equals absolute value of x has a basic rise and run of 1 up and over from the origin. There's no vertical stretch or vertical compression. There's no translation or reflection over the x-axis just yet. We're going to go ahead and see if any of 1, 2, or 3 does that for us. So the general equation in vertex form is f of x equals a times the absolute value of x minus h plus k. A happens to represent that vertical stretch factor, where if a is, say, 2, we'll go up 2 over 1 from the vertex. If it's negative 1/2, we'll go down 2 over 1, down 1 over 2 from the vertex. H and k represent the vertex. Now, h is subtracted. So if you see a minus h inside of there, a minus 2, for example, you'll move 2 to the right, not to the left. If it's a plus, you'll be moving to the left, not to the right. Whereas k, whatever the sign is where you go. Plus is up, minus is down. Now, it also represents your translations, therefore. It's not just the vertex, it's theoretically every point. But since we graph them that way, since we graph the vertex first and go from the vertex, then that's kind of how we talk about that. But translations go h units left to right and k units up, down, depending on the signs. So let's go ahead and jump in and get started on this. Problem number 1, we have f of x equals absolute value of x plus 5 plus 4. They do ask for us to describe the transformations before we sketch its graph in relation to just the absolute value of x, which is, once again, vertex at the origin and up 1 over 1, no reflection from there. So compared to that graph, what are we doing here? Well, we are, type it like this, we are not vertically stretching or compressing or reflecting, but we are translating 5 units to the left, and 4 units up. So those are the two things that are happening in comparison to the original function. Now let's go ahead and sketch this graph as well. I don't know if there's a way for me to stay completely zoomed out, but since I'm no lower than the origin anyway, I can probably do that. That looks okay. So from here, we are going to go ahead and 5 units left, 4 units up, negative 5, comma 4 is the vertex of this graph. Just like the absolute value of x going up 1 over 1, like so, we are also here going to go up 1 over 1 to the right of the vertex and to the left of the vertex. So that's the appearance of this graph with some poor dots, but that's what the ruler portion's for when we sketch this function, like so. Try our best. Did they ask for domain and range? Does not look like it. So I'm not going to answer something that's not asked, at least not at the moment. And that is number 1. Number 2. G of x equals negative 1/2 times the absolute value of x minus 3 minus 6. Okay, On number 2, we now have A, represented as negative 1/2. Both the negative and the 1/2 have two different things that affect your description as well as your transformations in general. From the negative portion, that's where we reflect over the x-axis. I think the book says it like reflect in the x-axis or something like that. Totally fine, but that is the statement we make. We also vertically compress by a factor of 1/2. What that means basically is instead of going up 1 over 1, we will now shrink half that height, up 1/2 over 1, or as I said before, up 1 over 2. Sorry, down, because we're reflecting over the x-axis. That's what the negative is mentioning. Let's bullet point these if we can, because now it's different things happening based on parts. Now we still have H and K. I could probably state them in this one portion of the sentence here. Translate how many units right, left, and up, down. We are going to translate 3 units right. This is because it's a -3. You plug in 3 to get 0 in there, and you get -6 out, 6 units down. So all 3 transformations types are being applied: reflections, compression stretches, and translations. And I'm going to go ahead and do this graph. And hopefully, again, I can't really fit this all on one screen at one time. I'm going to have to kind of go back and forth. It's just the nature of the drawing and such. I could be better about it, but currently I'm not. So let's go. 6 units down. So let's copy and paste that, actually, if that's okay. Sorry, I'm thinking about how to get this problem represented. All right. So -1/2 x minus. So 3 units right. So 3 -6. 3 -6 is the vertex. We will go down 1, right 2, and down 1, left 2, because of the -1/2 slope. That's the reflection portion. And we draw the line. We draw the line. And that is the drawing for that guy, number 2, with that instruction. Sorry for not being able to fit it right. Some of this isn't always logistically perfect. Okay. Okay. Give me one sec. There we go. Okay. Number 3. H of x equals absolute value of -x plus 2 minus 4. Now you have to be careful with this one because it's not quite in its absolute value form right now with that absolute value of x minus h bit. This is a negative here, which means that a might not be its true a, or this might not be its true h, and things like that. You have to be very careful. So before we actually start describing it, let's first kind of rewrite this. I'm going to factor a -1 out of here. And, you know, I was thinking about this, which is a little rough. Obviously, the book is assuming you're going to be using a table of some sort. And, I mean, I'm just going to go ahead and say it. That's what they're assuming you're going to do. When I say the word factor, you might actually not know what that means because it doesn't appear until Chapter 2 in the Integrated Math 2 section. Factoring is the opposite of distribution. And the concept of factoring, it's kind of like dividing to your multiplication. I realized that when I was doing the section 1.1. The concept of this is factor a negative out of here means I can distribute negative back in, and I get this. It takes practice to figure out what to do. Maybe you're doing these problems, maybe not, but that is the factoring portion. Now that also means that's a -1 that's multiplying by that x minus 2. So -1 is being multiplied, and you can separate them as 2 separate absolute values like that. And the absolute value of -1 is +1. And when you multiply 1 by anything, it just becomes that thing. Therefore, this is a different rewrite of that exact same equation, but now it's actually in vertex form. And although there seems to be no actual difference in A, there is an actual difference in H. It doesn't go 2 units left, it goes 2 units right. 2 is the number that you would substitute into here to make this 0 and to minimize your values. And that's true, as you can see here. H is 2, K is -4. So there is no vertical stretch or compression. There are no reflections. We are just going to translate. We will translate 2 units right and 4 units down. So that's the description of that, and we are going to make its graph as well. As Well, aha. Let me shrink it a little bit. Okay. Whoops. Hold on. I lost everything. There we go. Okay, can you see that? All right, let's try this. So we are going to go 2, -4. And we will do a rise and run of 1 to the right and to the left. Because the a value is 1, no change in those transformations. And you can tell it truly was 1. We took the absolute value of -1, which became +1. If you'd like to see more questions like that, of course, I did some in the section 1.1 problem set. And there is the graph in the V-shape. So I think those are the only 3 that I'm actually graphing so far for absolute value functions. We'll see what else they have in store for us moving forward. Okay, numbers 4 through 7. Still absolute value, section 1.1. Write an equation that represents the given transformations of the graph of f of x equals absolute value of x. So this time they are giving us the transformations. If we determine what a, h, and k are, we will write it in, once again, this form based on what they state. So let's take a look. Number 4, horizontal translation 9 units to the right. That means our h value is 9. That means in our equation, it's going to be written with an x minus 9 in there because it's x minus h. That means that a is 1 and k is 0. Assume by default a is 1 and k is 0, meaning we aren't going to write them unless anything changes on them, even if it means making a negative. So right now, h equals 9 is the only change in this. That makes this f of x equals the absolute value of x minus 9. Nothing else changes compared to the original f of x equals absolute value of x. Number 5 looks to be like a single transformation as well. It looks like most of these actually are. But if I asked for like 4 different things, you'd want to be prepared for them. Vertical translation 4.5 units up. That affects k, and it is a positive 4.5. Go upward plus k plus 4.5. This will say f of x equals the absolute value of x, close that, and then plus 4.5 like so. That is the k. That is on the outside of the absolute value function. Number 6. Horizontal stretch by a factor of 5. Now, I have not referred to horizontal stretches and compressions. Very specifically, A is a vertical stretch factor. So 6 is a little bit jarring, perhaps, compared to the videos I've done before. Let me get into this as best as possible with you. A horizontal stretch, if you can imagine, let's bring a graph thing over. There are other ways to refer to this. Sometimes they use the letter B. You know how there's A, H, and K? Sometimes there's a B that's in reference to it. I will reveal that one, but first I want to kind of just bring up what this thing is. Sorry, there's a photo that popped up as a text, and I see it's a photo of one of my siblings holding a guinea pig. So I might want to look at that at some point. Looks kind of adorable. So if you know that, normally there's an up 1 over 1 component, right? And the vertical stretch means, like, if we vertically stretch by 5, I would say up 5 over 1. Well, a horizontal stretch would be every time we go up 1, we'd go over 5, like that. Boom, boom, and boom, boom. So what happens instead with a horizontal stretch, you can see that it's the equivalent of a vertical compression. When I say up 1 over 5, that's the same thing as A being 1/5. It's still a rate, how much we go up versus over. A vertical stretch was up 5 over 1, because instead of the up 1 over 1, you multiply your rise or your fall by that certain factor. But a compression can be the other way around. It's what you're dividing by, essentially, how much you run compared to that rise of 1. So one version of this is still writing this with that in mind, which is, whoops, I locked it, which is an A value of 1/5. That's what gets you your horizontal stretch. So that's one version of this that we'd be looking at, which then gives you f of x equals 1/5 times the absolute value of x. Now, when they use b's inside of here, they do have that inverse component applied, and it's exactly as you just saw. I'm putting it on the outside because of its appearance and what we're doing with that. There are some books that'll have this form, but instead they will either put a B inside here just like that, straight up. You'll have to note that B gets flipped the exact same way that H gets flipped, meaning it's minus when it goes to the right. B, when it's stretched, it becomes like 1/5 instead of 5. And some books actually put it as a 1 over B as a reminder. Gets a little awkward that way, but if you know how that graph works, we can put it that way. And keep in mind, we can factor the B out. We can take the absolute value of that B and bring it on the outside. I know it's a more confusing question based on its nature, but that is what we have. With a horizontal stretch, it's also the same as a vertical compression. Number 7, vertical shrink, I say compress, vertical compression by a factor of 1/4 and a reflection in the x-axis. Now, the compression by a factor of 1/4 means literally still 1/4. The idea that it's a compression, this is also the same as horizontal stretch by a factor of 4. Reflection in the x-axis means this thing's going to flip over like that. No h, no k, that's different in comparison. This is f of x equals negative 1/4 times the absolute value of x. I think arguably an easier question than number 6, all depending on what you're looking at. I wish they combined some of them together. They did not, but we described some of them combined together on numbers 1 through 3. Okay, numbers 8 and 9, we are going to graph these piecewise functions. This is section 1.2, and then we will describe the domain and range. Okay. Oh, I guess range is going to be new. I was going to say the domain is likely all real numbers, but I take it back. Here's a piecewise function that is not. Excuse me. Okay. We are graphing, right? Number 8, y equals either 3/4 x plus 1 when x is less than negative 4, or it equals negative 2x minus 3 when x is greater than or equal to negative 4. So the concept of this is you have two different slope-intercept form equations, y equals mx plus b, boom, and y equals mx plus b, boom. We are going to graph both of these, but we will limit where they are graphed themselves. What I mean by that, give me one sec, I'm trying to paste in a graph. What I mean by that is these graphs don't go forever left and right for both portions that are represented. They only go so far to the left and so far to the right, depending on what's displayed here. If x is less than negative 4, that means that this portion is going to be graphed only to the left of negative 4. And when x is greater than or equal to negative 4, that means everything negative 4 and to the right of it will be graphed with this in mind. Now, there are different ways these are done. I will mention a way that I had not mentioned in my video on section 1.2 at the time, but first I will begin with the way that I mentioned at the time. Y equals 3/4 x plus 1 has a y-intercept of 1. You might want to use a pencil for this, by the way. A y-intercept of 1, and we would generally rise 3, run 4 like that. But keep in mind, we are only graphing points to the left of negative 4. So you might want to do the whole go down 3 and left 4, because this is where we're going to find some of our actual points for the graph. Now, if this graph were drawn in full, it would actually end up looking like this. But we are not drawing the entire line. I might have miscounted that last one. Goes right there. We would draw the entire line like this. But this graph is not going to have the entire line. It's going to be crippled and limited just to the left of negative 4 on x, which is right here. So I'm going to feature this with an open circle like that. We do not include negative 4 as one of the points in this portion of the piecewise function. And furthermore, I am limiting how far this goes by shrinking this down to just that amount. So that's what you would kind of do. I mean, you don't have the tools to do exactly that, but what you'll do is you'll erase any points that you don't intend on using, such as these. I'm erasing all those, and you're only going to include the points that you do intend on using, such as these ones here. So everything to the left of negative 4 will behave like that function. Anything to the right of negative 4 will also behave like that function, but it looks like it's going to go, So over here, negative 2x minus 3. I'll draw that in blue and this in green. Negative 2x minus 3 has a y-intercept of negative 3 and a slope of down 2, right 1. Down 2, right 1 like this. And I can also go up to left 1, and I should. I should go up to left 1 as far as -4 on x, like that. I shouldn't go any farther because that's where we should start applying the top function. So if I sketch this graph here, it's going to look like that. These are the two components of that piecewise function. They look like that in total. I will go ahead and get these as a single color in just a moment, but I wanted to make sure that you saw exactly this. And that is the piecewise function we have. Now, the alternative way to do this, I would still do the green one the exact same way as I did because I can hit the y-intercept as one of my points. But the blue one got a little weird because I had to erase points or visibly trace that, like, I start here, but I don't want to draw anything, and then I go till I find a point. What is also another way you can do this is you can find that point first by plugging -4 into here. I know that seems counterintuitive to plug -4 into somewhere they say don't plug in -4, but the point is to find the boundary point, the actual open circle. If I substitute -4 into here, I get 3/4 of -4, which is negative, I don't know what that is, -3, plus 1, which is -2. So you plug in -4, you get -2. Boom. I could plug in -4 into this one. -2 times -4 is +8, -3 is 5, and I get that point. And then you just apply your slope the rest of the way. So it's almost like a point slope form, where you find out what the point is when x is -4, and then you apply the slope the rest of the way. I'm going to continue on the way that I had it before, the way you just saw. I hope you're pretty comfortable with it, and let's just fill it all in as black, so you see it as a single piecewise function like that. That is number 8. We are also going to be doing the same thing for number 9, but number 9 is not the standard piecewise function, it is a step function. So let's go ahead and check out number 9. I'm going to make sure I can fit the graph first. I can't. Let's do this on the next page. Okay. All right, number 9. We have y equals, and the following. Oh, 4 lines? Okay. Y equals -3 or -2 or -1 or 0. If we're looking between -4, oh, you know what? Before I keep moving forward, I'm sorry. Let's do domain and range. Give me 1 second. Okay. Number 8, once more. Domain is all real numbers. Domain is all real numbers. This graph goes forever left and forever right. There's no x value that is not included in this set. If you can believe that. You say -4 is not included, it's included right there, and everything to the right and to the left. The range, the y values only go as high as 5, and it hits every point below that, every y value below that. Once again, if you believe -2 is not hit, I can show you right there that -2 is indeed hit. But 5 is the absolute highest that this goes. So y is less than or equal to 5. Okay, now I'm going to move forward to number 9. And on number 9, we have the following. -3 is the y value between -4 and -2. And that hits -2 between -2. Whoops. Between -2 and -1. And then it hits -1 between -1 and +1. And then 0 between, move that, 0 between 1 and 2. Now, I'm mentioning between this and that, the left side is included on that set, the right side is not included. So you'll see open circles on the left, closed circles on the right. These are constants, which means they're flat. Y equals -3, y equals -2, y equals -1, y equals 0. They are straight horizontal lines going across in certain sections. Between -4 and -2, y equals -3. Literally, that means that right down here, between -4 and -2, y equals -3. Closed circle on the left, open circle on the right. And it's just going to look like that. And then it goes straight. I might want to use the line tool, but it just goes straight across there. So it'll look like that. That's the first part of this. So I have to kind of keep going up and down to see what I'm able to actually see on the screen and what I can't. So perfect, as long as you can see that. The second one y equals negative 2 between negative 2 and negative 1. Here's negative 2. Here's negative 1. Here is y equals negative 2. It's that straight line. Going just like that. These are step functions where it's just going to be kind of a step ladder, up and up. Y equals negative 1 across x equals negative 1 and x equals positive 1. And then y equals 0 between x equals positive 1 and x equals positive 2. Closed circle here, open circle here. And we sketch right there. So that's the appearance of this graph and this step function. The domain is not all real numbers. This only goes as far left as negative 4 and as far right as positive 2. Notice that positive 2 is not included in this set. But it hits every x value between negative 4 and positive 2. So we'll write it like a compound inequality, just like that. This range is a little bit trickier. It is not an inequality of any sort because we don't hit every value. See, we hit negative 3, negative 2, negative 1, and 0. We don't hit anything in between them. We don't hit negative 2.5 or negative 0.7 or anything like that. We only hit those numbers. These numbers literally are the only y values that are ever touched. Nothing in between. And that's how we write it. It's actually a set, negative 3, negative 2, negative 1, and 0, like that. It's a discrete set of only those numbers. We can't say between negative 3 and 0 because that would imply that we are also hitting all the decimals in between, and we're not. But that is the domain and range of number 9. I'm sorry that I didn't move this thing back over. I feel bad whenever I don't actually do the things like I intend to. But that is number 9. It's written as such, and there we are. All right, number 10, write a piecewise function represented by the graph shown. So if you look at that one on number 10, number 10. If you look at this that's drawn over there, that's what we're talking about. We have to be able to write that out, which means we have to be able to track and trace what's going on and where it's restricted and such. I'm going to write it in f of x function notation. You can see it's broken up into 2 different behaviors. They are broken up where x equals 2. So to the left of 2 and to the right of 2, we do 2 different things. So I'll just go ahead and write this first. I'm going to say like when x is less than 2, and over here it's when x is greater than or equal to 2. That's really what we're breaking up here. The less than 2 because it's the open circle, greater than or equal to 2 because it's the closed circle. So when it's less than 2, we want to find out, hey, what's that y-intercept? It looks like it's negative 1. So in mx plus b form, it's something x minus 1. The slope, it doesn't look like up 2 over 1. It looks like I have to count up 1, 2, 3, 4, 5, and over 2. We have to rise 5 and run 2 before we hit another integer point. So it looks like it's y equals 5 halves x minus 1 on that side of the graph. And I firmly believe that is what the answer is. And you can check on the other side. The next graph just looks like a down 1, right 1 slope. So negative 1 slope. So negative x. And what you'd want to do is track the slope backwards to the y-intercept. Up 1, left 1, up 1, left 1, all the way to positive 4. So negative x plus 4 is the other graph, which only, once again, pertains to that portion of it. And that should be number 10. I think that's it, unless they're asking for anything else. No domain and range is asked for. That's it. Number 11. Also in section 1.2. Write the function y equals negative 4 times the absolute value of x plus 1 as a piecewise function. Now, we've done absolute value functions. This is that absolute value form with a, h, and k involved, however they're written. What you might want to do on this one, you don't really need to like draw the graph, but you might want to sketch to represent what it looks like to make sure that you're fully aware. This is at negative 1, 0, and it goes down 4 and over 1 both directions, like that. Boom, boom, for the idea of the graph. So to the left and to the right of negative 1 is where there's different behavior on the graph itself. That's the important aspect of it. So to the left of this portion, because this is what that graph looks like, y equals negative 4 times the absolute value of x plus 1. So as a piecewise function, what you'll do is split this up into 2 different parts. On one part of this, you have to the left of negative 1, say like that. and then to the right of -1, you have something else. Now, you only use the or equal to in one of these and not the other. Which one won't matter because it's the same point that's considered here. So what happens on the left side of -1 is you have a slope of +4. Notice that it's a rise of 4 and a run of 1 this direction. So we're going to say 4x, blah, 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 blah. And to the right of -1, it goes down 4, right 1 appropriately, where you'll see a -4x. Now I'm going to finish this one first because I can see the y-intercept is -4. On the right side, remember, the y-intercept is crippled as far as I can't see it. Up 4 over 1, that's the x-intercept. Another up 4 over 1 right there would have been +4 y-intercept. So 4x plus 4 like that. It's really all about tracing where it goes. I think it is important to get a sketch of that graph to make sense of what you're doing, and then we can write it out, and this is what the answer actually is. So as an absolute value function, an absolute value function graphed as a piecewise function, in this case, looks like that. All right, number 12 is out of section 1.3, and it looks like we're doing 1.3 also for 13 through 15. But let's begin with this one. Find the inverse of the relation shown in the table. So number 12, the original has, I'll just put x and f of x as your input and output, which is written as -4, -2, 0, 2, and 4, and 6, 3, 0, -3, -6. Finding the inverse means x's and y's swap. I'm partial to using inverse notation and writing it like this. So your new inputs and your new outputs are now swapped. So anything that was a y is now an x. 6, 3, 0, -3, -6. And these are now the y values. And that literally is what happens. Whether you write it as a table, you have it in an equation, a graph, a mapping diagram, a set of ordered pairs, x's and y's swap. What was input is now output and vice versa. And that's it. This is the answer to question 12. Numbers 13, 14, and 15 are still in the inverse section. We are going to find the inverse of the function, then graph the function and its inverse. So on number 13, we have k of x equals -1/2 x. I'll graph them at the end. I'm going to begin by turning k of x into y. F of x means y, and that's what I can write. Now I'm going to go ahead and take the inverse of this. Taking the inverse means x and y swap. You just saw that on number 12 for a completely different reason. But x and y swap. Now this will say x equals -1/2 y. The goal is to now resolve for y, so you have an equation in slope-intercept form, or where y is the dependent variable based on x, because they're represented by the same graph. So we want to get y by itself again. We divide both sides by -1/2. That's also the same thing as multiplying both sides by -2, like so. -1/2 times -2 is +1. So we're left with y equals -2x. That is that equation. If I write it in inverse notation, it'll look like that. Still the same answer, but this will go ahead and be noted as the inverse to that graph. Now, what an inverse means is when graphed, and I'm going to go ahead and have to shrink it to fit it right over here, but when graphed against a function against its inverse, they are both reflected across the line y equals x. The line y equals x is this guy right here, this diagonal line. And reflecting across that line just means that every point that you see on one end of it swapped on the other side is the other set. So when you look at what I'm graphing in blue, -1/2 x is in y-intercept at the origin, and down 1 right 2 like this. This one's maybe not as unique as some other ones you'll see. In fact, none of the linear ones are completely unique. I love seeing the curved ones in comparison, really. But this graph looks like, hold on, I'm going to get my settings right, in blue. That's the original. Now the inverse, I'll do in green, is -2x, down 2, right 1, like this. These points have x's and y's swapped in comparison to one another. I'll circle and highlight some of those and show that that's how you can always graph an inverse if it gets a little tricky to graph, because especially if it gets a weird y-intercept, or just if you already have the original graph. So those are the two graphs. If you kind of tilt your head, you can see where they have that reflection across this line, y equals x. Let's highlight a specific point and see where its inverse is, see if it makes sense. This point right here is the point -4, 8. That's from the inverse. If you get to the original, x and y should swap, and there should be a point that is 8, -4, which is right there. They indeed exist. 8, -4 was the original xy. Swap the xy, you have -4, 8 as a point. This is all over the place. They all have those, but you can see the reflection across like that. So that's how they look as sketches, and that's an example of one that has a point reflected across. That is number 13. Number 14. P of x equals 3x minus 5. Okay. We will turn P of x into y, and we will do the exact same things we saw before. We will apply the inverse by swapping x and y, and we must solve for y again, get it in that slope-intercept form. I will add 5 to both sides to begin with. Then I'm going to divide both sides by 3. Now I'll show you what that first looks like. You would divide everything by 3 like that. And now you have y equals x plus 5 all over 3. It's best that you split this into two different parts, x over 3 plus 5 over 3, as far as slope-intercept form goes. This is not wrong, by the way. I do intend on graphing it, but I want to show you what it looks like with its proper slope and all. I also want to turn this into inverse notation like that. X over 3 is the same as 1/3 x, right? 1/3 times x is x over 3, and there's 5/3, which is not my favorite y-intercept in the world to go off of, and this is a perfect example of how I'm going to use the original function to help sketch this other graph. I will apply the slope, but you can do that with all your other points as well. You can swap all the x's and y's. That's kind of my plan within. Let me get this. I'm trying to get this line and this part of the graph together. Did it work? Sorry, give me 1 second. I don't think it's working. That's okay. Oh, it did work. Perfect. Okay. Okay. So, let's sketch these. The blue will be the original. -5 y-intercept. Rise 3, run 1. And fall 3, run 1 to the left, like this. We will get this graph, this line. That's the original. Now, I plot the points a little small behind this line, but pick a point that you see on here. And okay, before I say that, if I wanted to do this one, I would have to use the 5/3 y-intercept, which is 1 2/3. I don't love that point right there, especially when I have to count up 1 over 3. Instead, I'm going to choose an integer point. Remember, the integer points on this graph here are inverses of the ones on here. So pick a point on here that you like. Let's say the point 0, -5. Flip-flop those points. There should be a point that's -5, 0. Your inverse will include this point among all the points that are there. And this is a straight line with the slope of 1/3. You don't have to be on the y-intercept to plot your rise and run up 1 over 3. You could be right here and do the same thing. Up 1 over 3, up 1 over 3, and you can continue that. And this works just as well as all the other ones. Like I said, you also don't have to apply the whole slope. If you just want to reflect all of these points, change the x's and y's, go ahead. That totally works. But if you think you know your up 1 over 3 slope, I think that'll be just a little bit faster. And guess what? This one does cross y equals 5/3, y equals 1 2/3 right there. It crosses it. I just didn't have to plot it as a point and count using that slope. All right, then we have number 15. Still the same concept. They do have a decimal written out. Let's look at this. I would generally like to rewrite this one in some way. First things first, I will turn this into y. Next, before inverse or anything else, I want to get a good rewrite of this equation. -0.2x plus 6. Let's put the mx plus b here. We like seeing fractions for our slope, so we know our rise and run. -0.2 is also negative 2 over 10, which is negative 1 over 5 as a reduced fraction. So I can write this as y equals negative 1/5 x plus 6, like that. This is not the inverse. This is just the equation written better. So this is also that. When I graph this, I'm going to be using that as my source. Now, maybe you prefer this appearance when it comes to solving for y. I don't know. I'm going to go ahead and go off of this one, though. It's more common to be referenced. All right, let's get to that inverse. We're going to swap x and y. X equals negative 1/5 y plus 6. I will subtract 6 from both sides, or not. I will subtract 6 from both sides. And just like that one problem where we were we had a negative 1/2, we multiplied both sides by negative 2. To counter that, I have a negative 1/5. I'm going to multiply both sides by negative 5. But this negative 5 multiplies into the entire quantity, just like how when we divided by 3, we divided all of x plus 5 by 3. We multiply all this by negative 5, and the equation will now say y equals, if I distribute, negative 5x plus 30. Or inverse of r equals negative 5x plus 30. So there's a lot of work to be had on that problem if you want things to look proper, how you know best. Now I'm going to sketch both graphs, and there's a little bit of tricky stuff to them because one of them, sorry, I got to group these. There we go. Because one of these we had to get a rewrite for. The other one, we can't really fit that y-intercept, but we go right back to what I stated before. If you can't fit it properly, don't fit it at all. If you can't fit it properly, choose another point that's a reflection of this one, and you'll be good to go. So, positive 6 is the y-intercept to this one, and a slope of down 1, right 5 can be applied, or up 1, left 5. You have that guy. There. That is the original. The inverse, which will be in green, I can't fit 30. Sorry, I'm still trying to fix this. I can't fit y equals 30 as the y-intercept. It's way up here, but I will go down 5 over 1. You can count a certain number of times until you figure out what would go where, or you can pick a point that's also on here. That's a reflection. Instead of 0, 6, we could have put 6, 0. Hey, 5, 5. Instead of 5, 5, we could put 5, 5. Oh my gosh. They're both on the same point, and that makes sense. Anything that goes across the line should be, this is y equals x. Y and x are one the same here, and when they flip-flop, they're also one the same. So here are two of the points, and this seems to agree with the slope of negative 5, down 5, right 1. So I'll just go ahead and continue that. That looks pretty good. As long as you can fit a point, a plotted point that fits on there, it works out. And make no mistake, this thing will cross with a y-intercept of 30. We just can't see it in this window range if you're using the same graph paper as I have. They indeed look like reflections across that line with each other. I hope you agree. Okay, numbers 16 through 18. These are the last three. Section 1.1 on this first one, absolute value. The other ones are section 1.2. So let's take a look. Number 16, write two absolute value functions whose graphs form a square in a coordinate plane. All right, this is a little open-ended. I remember there being a question like this before when I was actually doing the problem set at the time, but they already gave us graphs and then we had to do something off of it. So this can get a little tricky sounding, but in order for this to work best, you are going to need, is it square, right? You are going to need an a value of 1 or negative 1. Like that's what we're going to have because a square needs to have, right angles, right? Like right angles all around. Boom, 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 boom. And they also need equal side lengths. So basically what we need, I'm going to kind of sketch the graphs first and then we'll write equations for them. And I'm going to go open-ended, like I'm going to go ahead and like plot them outside of, this range. Like I can plot a point right here and I can go that way, right? I'm going to go ahead and go up 1 over 1 that way. In order to do the square, the other one that's upside down will need to be directly above it. So maybe up here, and then we can go that way, and boom, we'll get a square out of it. And I'm fine with that. That's what I'm going to do. So I have this point here that is 4, -2 for this vertex. We will rise 1, run 1 like so. And we'll be able to get a bunch of points going this way. Now the other one will have to be directly above it to make it not a rectangle, but instead a square. And we are going to, they don't restrict domain and range, right? No. I don't know what I was talking about. But it needs to be directly above, because in a square, all sides need to be equal. But they also need to make right angles, which is where this comes from. So one of my equations is going to be, I'll call this f of x. F of x. We'll say f of x equals a, which is 1, times absolute value of x minus h plus k. So there's one of them. The other one, I need to plot somewhere directly above. I think I put about right there, but directly above, and it's going to go down 1 over 1 in order to get that square bit. Because it goes down 1 over 1 the same amount of times to hit points of intersection, these will indeed be congruent sides in this square. I'll highlight where that square is once I'm done with that portion. I want to draw the entire graph. I don't think it's required, right? They don't ask us to draw the graph. They just say write them. And then we'll talk about what we can do to write them in any format that you'd like. But this is just one example, and I'll call this one g of x, by the way. So this will be g of x equals -1 times the absolute value of x minus 4, and then plus 6, like that. So that's an example. This is open-ended. This is open-ended. So how can you do this in general? Once again, you need an a equals 1 in one graph and a equals -1 in the other. Because here's the problem. Once you use like 2 as the slope of 1, then suddenly that's not a 90-degree angle. That's pretty much the problem. 2 up 2 over 1 is not a 90-degree angle. So you need this. You also need the same h. The same h. It needs to be horizontally translated the same amount so we can be directly above and below. The last thing is, for this one, the k here needs to be greater than the k there. So the k values can be whatever you like, as long as they're not the same. Let's see. The k in a is greater than 1 needs to be less than the k in a is greater than, or a equals -1. This k needs to be a larger value so that it can go down and intersect with it, and it can't be exact same k value. So these are the 3 provisions that are needed, and you can make up your own any way you want, and then you're good. That's number 16. Okay, number 17. Describe a real-life situation that can be represented by the graph shown. Okay, I didn't plan this out, so I got to think about one that I particularly love. Currently I'm really a fan of that subscription model thing, because that does use time, and price doesn't increase during that time. And there are other things that you can argue would increase over that time, like in an hour or something like that when something happens, including if you're babysitting for an hour and a half, you might want to be paid for that half of that hour. I know that whenever I would tutor, we would adjust things like that. If I did half of the hour, if I charge this much per hour, take half of them, things like that. Subscription models tend to not do that. They also, though, would tend to not go $10 per month after the first month is $20 or something like that. But let's think of another one with that then. I'm going to pause because there's no reason for you to just watch me sit and think. I just want to think about it. Okay, so I just thought for a second. Here's what I want to do. I'll do something where, because I'm trying to think of an upfront cost being more, and I don't think subscription things seem to work as well. I'd rather do something like parking, where on the next hour they charge another $10. So there are a bunch of things you can do, but I'll say you are paying for parking at an event. The first hour is $20, and every hour afterward is another $10 increase. Now, the idea behind this is you are $20 for the first hour. So the first hour is $20 straight up. The next hour is another 10 straight up, just like that. That's an example of it. The subscription model thing works. I just don't think that an upfront cost would be more necessarily, and I feel like this thing could. Subscription first month is the same as all the others. That's just my thought. Okay, finally, number 18. You are ordering customized bracelets for a fundraiser. The total cost in dollars of ordering X bracelets is represented by the function below, and you see that. I'll go ahead and copy that down. We have 0.9x plus 25 if x is between 0 and 100. 100. We have y equals 0.65x. I might have to use the calculator for this. Plus 25 when x is between 100 and 500. We have 0.4x plus 25 when x is between 500 and 1,000. And then we have 0.1x plus 25 when x is greater than or equal to 1,000. Okay, part A. Find and interpret f of 35. Well, f of 35, we are going to substitute in the set between 0 and 100 because that's what 35 is between. So 0.9 times 35 plus 25. 0.9 times 35 is 31.5, which is plus 25 is, I don't know why I'm having trouble with this, 56.5? 56.5. Now they ask you to interpret this. Ordering customized bracelets for fundraiser, total cost X bracelets. So if you order 35 bracelets, you will spend blah, blah, blah. So if you order 35 bracelets, bravelets, you will spend $56.50. It looks like that 25 kind of looks like an upfront cost for ordering. And then you can see you buy in bulk and you spend less per bracelet as a result. They incentivize you to spend more. Part B. Determine the costs of ordering 100, 500, and 2,500 bracelets. So we're going to do f of 100, f of 500, and f of 2,500. Now f of 100, we're going to substitute not in the top equation, but in the second equation because 100 is there. So we're going to do 0.65 times 100. Can you see that? Sort of. 0.65 times 100 plus 25, which is 65 plus 25, which is 90. So you order 100 bracelets, you'll spend $90. F of 500, we're going to substitute into this one. So 0.4 times 500 plus 25, which is 200 plus 25, or 225. That's how many dollars you'd spend on 500 bracelets. And, or sell, you're ordering for a fundraiser, the total cost. You're buying. And then 0.1, because 2,500 is more than 1,000. 0.1 times 2,500 plus 25 is, I don't know, I'm having trouble, 250 plus 25, which is 275. So you can see kind of the benefit of ordering more. See, if I order one bracelet, if I order 0 bracelets, I don't know why 0 would be a part of this. If I order one bracelet, I would have spent $25.90. Whereas if I order 2,500 bracelets, $275. Obviously, it's more money, but on a per bracelet basis, it's really cheap. It's almost 10 cents a bracelet, literally. It's almost 10 cents a bracelet versus $25.90. So interesting. All right, and then we have part C. What do you think? Okay, I already kind of said this out loud. What do you think the 25S? What do you think? Oh, the 25s in the function represent. The upfront cost of ordering the bracelet, but for you, since you're ordering them, it's probably a shipping cost. Okay, the shipping cost. That's my belief. Unless you're picking them up in store somehow. and it's a flat rate. No matter how many you order, that's still up front. The interesting part, and I wish they didn't have it, the interesting part is they do show that X could equal 0. Why would I order 0 bracelets and you ship nothing for 25 bucks? I would have preferred that they did this because you need to kind of order 1 bracelet, but that's okay. So that's my guess, shipping costs, and that'd be my final one. Okay, so that ought to do it for this one. I did get within the hour. This is Mr. Robinson. Thank you so much for watching. Hopefully you found everything you needed. If not, jump to the description section down below and you should find everything there. And you can find the other playlist videos in the IM2 Big Ideas Math set. All right, take care. I will see you in the next one.